that it's a tensile, this is not clear to me, but looking at the solution, what you have to interpret is that these are 30,000 pounds, and this is a length of 200 inches. You can see the author's solution technique here then to this. You have to interpret those words into that diagram. Let's go into the second one here, and hopefully this is better. What is the decrease of the highest of an 8-inch round, 16-inch high concrete cylinder when the unit deformation? So you start with deformation is equal to PL over AE is the first thing I would do. You have area or information to get area. Let's see where this takes us here. 8-inch round, so it's going to be pi over 4, 8 inches squared. Length is 16. And where are we going here? Unit deformation. Deformation is 0.0012. So, and this is concrete, so you can get the appropriate modulus out of that. So you can then rearrange this to solve for the force P, and then stress would just be P over A, which in A you already have. So that's all there is to that problem then. Let's go into the third one. Required diameter of steel if the tension load is, assume safety factor. So you're going to deal with that safety factor here, and we're going to assume that's applied to us. Assume this is axial loading again. Your allowable stress is going to be that ultimate stress divided by your factor of safety. So that's your 60,000 divided by the factor of safety 5, so that's 12,000 is your allowable stress. And again, that's set equal to P over A. If the tension load is the seventh. And then this is, so this is your 12,000, this is your load of 7,000, and you'll just solve for the area, and knowing that the area is pi over 4d squared, solve for d. So this one's going to involve Poisson's ratio, because I think we're talking about a punch here. This is 4. Increase, got a force of 40,000 pounds on a diameter that's 0.75 inches. So there might be better ways of doing this, but here's what jumps out to me. A lot of intermediate steps here. You can get the stress from that 40,000 divided by the area, which is going to be pi over 4, the diameter 0.75 squared, so that's your stress. It's steel, so we're going to assume it's elastic. Modulus is equal to stress divided by strain. And you can solve for strain here, which will be your axial strain. But you're talking, the question is about the diameter, so you're going to recognize that Poisson's ratio is equal to the lateral strain divided by that axial strain, so you'll need the lateral strain out of that. And that's the change in diameter divided by the diameter. So now that you know the lateral strain, you can multiply it by the diameter, get the change in diameter, and then add that. So you're looking for the final diameter, and that's the initial diameter plus the change in diameter. There might be an easier way to do that, but that gets you there. Okay, so let's go on to question 6, and hopefully this works out a little better. Well, we're going to have to assume this thing is elastic. We're looking for modulus, so if it's elastic, that's stress divided by strain, and hopefully you got enough information to get stress and strain here. So that's just my thought process on this. You're seeing this off the cuff here. Stress divided by strain. We know it's normal loading here. Do we have enough information to get each of these? We do. Stress is equal to the 1,000 pounds divided by the cable area, which is going to be pi over 4 times 5/16 squared. And strain is it elongates 6. It elongates it in Morse. 1,500 feet. So it elongates 6 inches, but to keep those units consistent, you're going to need that 1,500 feet multiplied by 12. So that's going to give you strain, and the modulus is going to be just stress divided by the strain.
Why wouldn't you include the 1,500 pounds for the load of the elevator in the stress calculation?
Oh, yeah, we should. We should. The elevator weighs. That's what happens when I read these too fast. Yeah, so this is going to have to be 2,500. 1,500 carries 15. Yes. Yep. Good catch.
Hope for the best.
Is that one good enough then? Okay, let's go on. I guess it's thermal stuff. They use only 1,500?
Oh, wait, the elevator's already, it's only calculating additional weight because the cable is already elongated by the weight of the
Oh, I see. Yeah. Boy, that is a tricky problem statement.
Yeah.
So, yeah, so it's only elongating from the weight in. The elongation information is only from the weight added to the elevator, which is 1,500. Boy, you got to read those pretty carefully then, huh?
Yeah. So we go 1,500 instead of 1,000.
Yeah.
I
Yeah.
hope that's not how the actual is.
Yeah. Boy, the problem wasn't very difficult, but getting the numbers in there right is different. Okay, let's see the rest of them this way then. Yeah, some of these are worth doing, and some of these you can almost do by inspection, which you almost need to do to save time. This is a shear diagram, and remember, as you go to the moment diagram, which is the question is about, it's the area under the shear diagram. So you need to be considerate about the area of each of those shapes and how they add and subtract to create the minimum or maximum values here. So if you're looking for the maximum magnitude of the bending moment, this is going to go down, and it's going to get down the area of this. It's a trapezoid, but really the average here is 13, so the height is 13 divided by 2, so that's going to go to a moment of 26. So now you're going to be concerned, so that's the biggest moment here. That's quickly you should be able to see that D is the answer to that. You may want to double check that to make sure the areas, none of the areas get more than that. This goes downward. You're going to be adding this area here. So you're going to be adding, what is this? I can't really, 6 times 6 divided by 2. And that's not going to take it above 26. This area here is going to go up. It's height of 4, run of 4, it's 16. That's not going to be bigger than a 26. So really quickly you can tell that the biggest area and the biggest moment is associated with that trapezoid, and it's 26. Does that help on that then? Mm-hmm. So this might go a little better here. You're looking at these things then. Let's look at this. Okay, this is looking for elongation, axial loading. This is just a PL over AE calculation. You have to make sure you get units straightened out here. That's probably the big exercise here. I would work everything in newtons and millimeters. So, I don't have a calculator, but that quickly should be deformation is equal to PL over AE. We'll quickly put in units right here. Your force is 5,000 newtons. We'll leave it that way. The length, is 0.25 meters. That's 250 millimeters. The area is given to us in millimeters squared directly, 1250. And E is 200 gigapascals. That's 200,000 newtons per millimeter squared. So that should give you the answer in millimeters, and I assume that's what the units are in the answers. Does that give you one of the answers? Yeah, okay, so it's going to be 5. If it's 0.005,
It's 5 micrometers.
yeah, that's right, yeah, okay. Yeah. Good on that one? Okay, let's look at the next one here. Well, you need to first of all get force from pressure times area. And again, you're going to have to be careful with units on that. So again, this is going to start with stress is equal to P over A, but that P is going to have to come from pressure. Force P is going to have to come from pressure times area. And the piston is 50 centimeters in diameter. And a gauge pressure of 1.4 megapascals. So that's going to be 1.4 newtons per millimeter squared. Area is pi over 4, and that diameter is actually 500 millimeters quantity squared. So that's going to give you a force in newtons. Is everybody with me so far on that then? This is going a little better.
550.
550 newtons. And then we're going to have to go back to the stress relationship. The stress is limited to, needs to be limited to,
68 MPa.
where's that at? 68 megapascal. 68 newtons per millimeter squared. And that force is 550 newtons. So that's going to give you an area. Yeah, and then that's what I was asking for, in millimeters squared. Now, and that's in meters squared, so you're going to have to move the decimal point by 6 places when we're done here.
174,289.
That's going to change things a little bit.
Just that. Oh, I didn't square the 500. Nice. That's better.
And then, so this divided by 68,
4,042.
4,042. That's going to be millimeters squared, but you should see recognize it's going to be A.
Yeah.
You got to move the decimal point 6 places. 4 times 10 to the minus, 40 times 10 to the minus 4. Yeah, it'll be the same thing. We'll see what happens here. In the following figure, value maximum shear stress is most near. Okay, so what's the first thing you're going to need to do here? Well, I would argue it's not even that.
Convert everything to the.
You need to know what that reaction is.
Oh, okay, yeah.
It's told you rigid support, but you got 1,000 going one way, 2,500 going away. That means you need 1,500 going this way on this thing. So you need to know that first before you do any cuts or anything. Shear stress in segment BC. I guess maybe you didn't need that. In fact, the value max should be. Okay, so maybe you didn't need that first, because as you make the magic cut in BC, you can quickly see it's going to be the 1,000 Newton millimeters, and that's just going to be a shear stress from TC over J. So let's make sure we can get a right answer for that. And again, you got to fix up units here. Shear stress from TC over J. Torque then is 1,000 Newton meters. I'm going to call it 1 million Newton millimeters. C is going to be to the outside surface, so that's going to be 75 over 2 to get the radius. And J, and then you're going to use the 75 millimeters squared for the OD, no, not squared, to the 4th power, and then the 50 to the 4th power for the ID, and I can't remember whether this constant's 32 or 64. 32.
Anybody watching the video, I'm gonna just like.
I think the question about the wood and the grain is just noise, and the extra information. So I think that still comes out to shear stress is equal to TC over J. 0.84. Yeah, so this shear stress then is 0.84 newtons per meter squared. 840,000 newtons per meter squared. That is 0.84 newtons per millimeter squared. So that's the way you'd want to use that.
It wants the answer in Newton meters.
Yeah, that may be fine, but when you're doing these calculations, I like to stick with newtons and millimeters and rearrange things when I'm done. That's the way I typically do it. So we're looking for torque, and our torque is going to be Newton millimeters out of this. C, does it give us a?
It's 100 millimeters.
That's going to be your 100 millimeters. And J again is your pi over 32, because that J is pi over 32 d to the fourth. That's 200. We need half of that for C in the top of this.
1,319, so C.
1320 Newton millimeters. What are they asking for units here? Newton meters, so
Yeah, that's what I got in meters.
oh, so you got 1.32 million Newton.
It comes out to, yeah, 1319468, so yeah.
Okay, so 1.32. Okay, I'm going to raise that then. So we okay with that one then? My preference is just when you're doing the calculations, take all the input in, do the calculations in newtons and millimeters. And even if you have to adjust things at the beginning and adjust things at the end, but at least while you know what you're doing, your calculations are going to work out right. Okay. So this is just a two-dimensional planar problem. Your maximum shear stress is going to be square root of stress x minus stress y over 2 quantity squared plus shear stress xy squared. So for our problem, x is a positive 40, y is a positive 20 over 2 squared. Shear stress xy is a positive 10 squared. So this is square root of 20 over 2, 10 squared, plus 10 squared, square root of 200. Sound 14.14, there you go. You okay with that one?
Yeah. I just think it's nuts that I haven't looked at that equation in over a year.
Yeah, it's etched in my memory. I did look at this problem here. This was this is our last one in this set here, and this one was pretty interesting. This one you can do by inspection. It's a little tricky, and it's a good question. I'm sure they put a lot of thought into coming up with this one, but you can do it by inspection. It's biaxial state of stress. More circle. Think more circle. Yes, I just saw in the middle you're going to have a compression of 10 and you're going to have a tension of 5, and the areas are consistent left to right and up and down. So as far as I could see real quickly, that what you have is a compression of 10 and a tension of 5. That sets up more circle here, minus 10 and a positive 5. Its radius, its diameter is 15, its radius is 7.5. That's your maximum shear stress. So that's, even without doing the area calculations, I could see it was 7.5 that quickly. Now, if you need more detail on that, what you have in the middle there is a stress element that's going to look like this. It's a compression, and the force is 10,000 newtons divided by an area of that thing, which is 10 by 100. And then here you have your tension stress, that is 5,000 divided by 10 by 100. And that gets you stresses of, did I do that? 10 by 100, right? Not 10 by 1,000. That gets you a stress of 10, a stress of 5, and you're still back to Morse circle with this diameter 15 and radius of 7.5. So that's a pretty clever problem. If you really understand biaxial state of stress and the resulting Morse circle, you can do that in a minute. But if you're floundering, that's
So doing it the Morse circle way, that gives us negative 7.5.
well. Okay. So they're asking for the maximum shear stress. Well, to get that, remember that's the
7.5 anyway.
what's that?
It would just be 7.5.
Right. It's going to be 7.5. Right. It's the same magnitude whether it's positive. Because Morse circle here is going to put you back here to minus 10 for the x direction, positive 5 for the y. This is your diameter. This is your radius. And the radius here is 7.5. Positive 7.5 here, minus 7.5. But that's the same shear stress.
Yeah, okay. That makes sense. I haven't done Morse circle in a while.
When I saw that, I thought that's pretty clever. That's going to test your knowledge of Morse circle. If you know Morse circle well, that's going to come quickly. If not, you're going to struggle a little bit. I would venture to guess you're going to see a lot of problems like that, where if you know what you're doing, you can do it in a minute.